All right, my purpose is to give you feedback on the thermal science quiz. And of course, this is for learning and growth. That's why we're here. The reason for the quiz is so that you can get data that shows you how well you are doing in terms of reaching course goals. The main course goal is to design experiments, and this quiz is really to tell you how well are you doing in terms of learning to build math models, and how well you're doing in terms of getting technical knowledge down. I'd like to share with you an idea I call the knowledge pyramid, and really talk about two ways to get knowledge. One way is to memorize examples, and there's an incredible amount of information to try and memorize. Another way to get knowledge down is to learn key fundamentals, things down at the very bottom of the pyramid, and everything above this point is built on these fundamentals. So the idea is by knowing a few fundamentals, you can understand a great deal about a discipline. What I have learned is ideas that form the foundation of a knowledge area are what is useful to get into long-term memory. And this is key for doing application. So I wrote this quiz to look at some very key fundamentals. That is very much ABCs, things right at the bottom of the knowledge pyramid. And I said, well, in thermal sciences, knowing real seminal concepts, knowing main equations, and I just picked one here. I picked the first law of thermodynamics because it doesn't get any more fundamental than that. And then the third thing I picked is working knowledge of units. Does one know the magnitude of various unit systems? Question 1, how big is a joule? Give a real-world example. How big is a BTU? Give a real-world example. And if you put anything at all that was reasonable, I gave full credit or extra credit. Here's some examples of how I would answer that. If we think of water, and we pick 1 gram, which is 1 cubic centimeter, and we want to put thermal energy in to increase the temperature by 1 degree C, this takes about 4.2 joules of energy, which is also, by definition, 1 calorie. If you can visualize a 60-watt light bulb, this is going to use 60 joules per second of electrical energy, and more correctly I can say that's a work term, and it's going to put out about 60 joules per second of thermal energy. And you can feel that if you put your hand right above the light bulb. If a person that has a mass of 160 pounds walks upstairs and changes elevation 10 feet, the change in energy can be estimated like this. So 160 pounds is about 70 kilos. So I just rounded that up, and I'm just using mg change in H for the change in potential energy, carrying cancel units. And that's about 3,000 joules of energy. So there's 3 examples. Now a BTU by definition is the amount of energy that will heat 1 pound mass of water. So we have 1 pound mass of water in a pan. That's about half a quart, so we can visualize a small saucepan on a burner, and that will heat it up by 1 degrees Fahrenheit. So that's the definition again of a BTU, the amount of thermal energy that will heat 1 pound mass of water through a temperature change of 1 degrees Fahrenheit. For the next question, I listed the first law of thermal because, hey, it's not about memorizing equations. And I asked for the name of each term, so that's fairly straightforward. This is the change in energy or change in internal energy. This is the heat transfer, and this is the work. But of course, knowing the names of terms really doesn't tell us anything. So the really key idea is, what exactly do these things mean? The way I might answer this is, I'd draw a box and identify this as a closed system. And I would state that we can talk about the amount of energy inside this system. And energy is a property that characterizes how much work can be done by the system. In very simple terms, how much weight can we lift through a distance? And there's only 2 ways to change the energy in the system. One way is doing work interactions at the boundary, And a work interaction in a thermodynamic sense is any interaction that's not heat transfer. So it can be force over distance, it can be electrical energy, it can be a number of things. The other way to change the energy in the system is by heat transfer. And heat transfer is the movement of thermal energy from hot to cold. So on this next problem, this involved air in a glass cylinder, and there's a piston here which is moved downward. And the question is, will the air get hot, get cold, or stay the same temperature? And the key engineering question is, why is this? And show how an engineer would answer this question. And of course, we know the air in here will get hot because this is how a diesel engine works. It compresses the fuel and that heats it up, and we get an auto ignite through the compression. And if you've ever pumped up a bike tire with a hand pump, you know if you touch it, the barrel of the shaft, it gets hot. So anytime you compress air, it gets hot. Now, why is that? To answer this like an engineer, I want to apply a main equation. So I'm going to define a closed system, which I've shown by a boundary here. And I'm going to define state 1, and that's prior to compression. And state 2, it's the instant after compression stops. And I'll assume an adiabatic process because, hey, glass is a really lousy conductor of thermal energy. And I'll apply the first law of thermodynamics. So here it is. The work is being done on the gas, so this is positive. And I assumed adiabatic, so there's no heat transfer. This term dropped out. So we're doing positive work, so the internal energy must go up. And the only form of energy that's available is thermal energy. And I believe we could just apply the mass of air times the heat capacity times the temperature change. And therefore, we can conclude that the temperature at state 2 is greater than the temperature at state 1. And I'd need to look in my thermal book and remember if I can actually use that or if I have to use enthalpy. But the key idea, it's just a real simple energy balance to show this. The next question just asks for some real simple definitions. What exactly do engineers mean by a system? So what's a closed system? What's a control volume? What does state mean? And what's a process? And these are just ideas that are used for analyzing millions of problems involving thermal sciences. So the system is simply whatever matter that the engineer selects for study. It can be a differential particle, it can be a volumetric region, it can be a tire wheel. It's just whatever it makes our life easy when we do an analysis. A process is a change of a system from one state to another. And a state is a condition of the system as specified by values of the properties of the system. A closed system is a fixed or identified collection of matter, and so it always has the same matter, and therefore mass cannot cross the boundary of a closed system. And a control volume, in very simple terms, is a geometric region that we define. We typically situate this geometric region around a pipe or around something with a flowing fluid. And if people had the ideas down in any kind of fashion, full credit. So this next problem involves an ice cube sitting in a cup of water in a room, and the idea is to build a math model to predict the time for the ice cube to melt and show how an engineer would do this. And the goal state is articulated here, algebraic equations written in terms of relevant variables like the mass of ice. Here's what the data showed. 5% of the students got the physics right and 95% did not, and they appeared to be just grabbing equations that didn't really apply to this situation. So I'm going to do a quick review of the physics. So if our system is 1 kilogram of ice and our process is to heat this from minus 10 degrees C to plus 10 degrees C, and we're looking at the energy change. So we have state 1 kilogram of ice at minus 10 degrees C, state 2, 1 kilogram of liquid water at plus 10 degrees C. We can plot the change in energy of our system as a function of temperature from minus 10 degrees to plus 10 degrees Celsius. And we see that there's some energy change to raise the temperature. Along this part of the curve, there's energy change to melt the ice, to go from the liquid form, from the solid form to the liquid form. And then along this part of the curve, we have another sensible energy change. So the really big picture idea here is there's thermal energy involves two things. Sensible temperature change, like right here, and latent change, like right along here, where we're changing phase. And for sensible energy changes, we typically use heat capacity and the basic equations written here. For latent energy changes, we use the latent heat of vaporization, or the latent heat of fusion, which is this property here. And the basic unit analysis is there, the change in energies in joules. This term right here has units of joules per mass and mass units there, so we can see how the unit analysis works out. So to build the math model, I neglected heat transfer to the air because that'd be very negligible compared to the heat transfer to the water. I selected the ice cube as a closed system, made some assumptions. Defined state 1, I have solid ice. State 2, the ice is melted. Applied the first law to my system. There's really no work interaction of significance. And so the change in energy is just how many joules does it take to melt the ice. And to get the thermal energy, which entered the closed system, came across the boundaries, I use Newton's law of cooling, convection, and that has units of joules per second, so I multiply by a time interval to get joules, so that both sides of the equation have units of joules. Now right here I've talked about how I would analyze each term, and notice my goal appears right here. And when I go through that term-by-term analysis, I have one equation, one unknown. Super easy. And the knowledge needed to solve this problem, one typically can find in a chemistry book, or in that'd be a freshman chemistry book or a freshman physics book. Okay, as you look at your score sheet, there's two things. One, there's a number of points out of 10. So this student received 8.5 out of 10. And this is grade stuff. And I'm not really that interested in that. The other thing you'll notice is your performance. And this is really telling you, how are you doing as an engineer? And this student, in terms of getting knowledge down, is at level 4.5. And in terms of building math models, is at level 4. And my abbreviations, that's getting knowledge down, and that's building math models. So if we look at level of performance, competent is at level 4.5, and if you're above level 5, you're excelling at doing engineering. On track is level 3, and not yet or beginner is level 1, 2, or 3. And so if your score here is level 1 in building math models, that means you're starting to develop some basic competence, but you're not really at the level you want to be for being an engineer. And similarly, if you're at level 2, you're still in the beginner category. And if you're at level 3, you're on track, but you're still not quite where you want to be. As a teacher, I want you to have data so you can see how well you are doing in terms of reaching the course goals. And we picked two really important goals here, getting knowledge down and building math models. Now, what the data shows is that 5% of you are on track and 95% of you are not on track. And of course, I've been taking data all semester, so I have a great deal more data to base this conclusion on. And I've been teaching 25 years, and I've seen this going on for as long as I've been in higher ed, that most people are not really learning how to do these things, so it's not a big deal. But here's kind of where you are as a group. Now some more professor talk. Virtually 100% of you can reach course goals if you choose to. And the course goals, again, are doing killer experimental work, getting technical knowledge down, and building math models, and doing this in a real simple, easy way. And you might be going, that sounds ludicrous, but actually it's not. There's a secret sauce. And the number one element, the number one ingredient of the secret sauce is believing in people. And in particular, other people have gone before you and done engineering and figured out how to do it in simple, easy ways that work and that are fun. And this is the community. And all the stuff I show you in my classes, I go out and talk to hundreds of engineers. I read hundreds, if not thousands of papers, just simply trying to find what has the community figured out. And that's the stuff I show you. So the number one secret sauce is just simply believe in the community of engineers and choose to do the same things that they do. The number two secret sauce is to reflect on your experience and then always learn and grow. And what you want to do is just take little baby steps. Look at this quiz and say, what can I learn? What are my next steps? And have fun. Hope you've enjoyed this video. We'll see you next time.